So, welcome everybody. Thanks for joining us today. We're very excited to show you what we've been doing recently with AI, and we think we're going to show you a sort of a world's first here, a foundation model specifically for pump simulation, and first widely available one. You can go and try and use, and we'll tell you about that at the end of the presentation if you'd like to go and try this. So. I think we promised some audience participation, and we're going to be looking to you in a moment to see whether you feel ready for this kind of wave of innovation that's coming our way. I think for some people may feel like they're already surfing down the wave. Some people are still paddling out to it. Some people are maybe waiting for the next one to come along. And we'd like to know really what you're doing at the moment. I mean, how are you using AI to accelerate various different things that you might be working on. So, as the first one, research. If we could have a quick show of hands just to see if you're already using AI tools, maybe LLMs, to do research at the moment.
Two.
Couple.
Anyone else?
Yeah.
We won't tell you university, don't worry.
How about writing? For improving writing, drafting. Yeah, super useful, right? Yeah.
It always surprises me with that, actually. I think I've written a really good email, and then I put it through ChatGPT to see if it can be improved, and then it's always better.
Yeah, it's hard to say no. And how about simulation workflows? You got one? 1.5? Yeah. Cool, okay. It's good. So, maybe take a moment to introduce ourselves. So I'm Alex, this is Steve. Obviously, we're from SimScale. We're both engineers. So Steve, you have a background in aerospace design.
Yep.
Before you came to SimScale. My background is in Formula One aerodynamics, of course, for simulation. So Steve is leading the application engineering team at SimScale and partnerships manager. And I'm a product marketing manager. So, I'm afraid it's time for a little bit more audience participation. Do you think we could just quickly introduce ourselves and maybe say sort of what your experience is with AI in simulation? Very, very, very briefly, if you've been using it, if you'd like to use it, maybe you've run a proof of concept, and quickly what you'd like to get out of this session. How does that sound? Good? Yeah? Okay.
Who wants to
start? Should we start with you, sir? Cool. All right. Yeah. Well, thanks everybody for introducing yourselves. It's really interesting to hear, hear what you're thinking at the moment about AI, and we're certainly here to share, our vision and show you also what it looks like in SimScale. So, on that note, I guess a brief introduction to the company. I'm not sure how many of you are already familiar with SimScale, but we are a simulation provider. We have over 600,000 users worldwide. We're fully cloud-based, so those users can very easily use our tool from anywhere, any device. We've got customers, in over 50 countries and thousands of academic institutions. We've been around for, I think, about 12 years.
Yeah.
And we've over 160 employees now. It's fluids and structures, electromagnetics.
Yeah, we're adding new solvers all the time. But, yeah. Hi.
Hello. Yes.
Was it?
Yeah.
It's a long walk.
It took me a while yesterday to figure out what this was. No problem. And there's a few examples of some of our clients. They're listed at the bottom of the slide. And so our mission is really making this high fidelity simulation truly accessible. As I said, cloud native at any scale. So this is what the tool actually looks like, and I think one of the main impacts that it brings to our customers is that they're able to reduce their simulation lead time and turnaround time really by like an order of magnitude. And so you can see some of the key features here highlighted. As I've mentioned a few times already, cloud native. You can see also there's you can actually do co-editing, similar to Office 365 or Google Docs or something like that. Collaboration, so very easy to share models. Has broad physics coverage, highly scalable, of course, being in the cloud. You're very much kind of removed from all of those kind of typical logistical headaches that you might find with kind of desktop CAE tools. So because it's cloud native, you're doing everything centrally. Build all of your workflows centrally. All the physics is there, the methods, the full workflow from CAD, pre-processing, simulation, post-processing is all there in one place. This allows you to have very good control over your sort of templatization and best practices, and you can deploy that broadly across your organization. Mentioned the collaboration, ease of collaboration in the tool, so you can easily share projects between users. The whole thing is, of course, done through the web browser, so everyone's getting really like exactly the same user experience, no matter who they are in your company. So the whole thing is very frictionless. And then crucially, for what we're here to talk about today, the AI infrastructure is also built into the same platform. So it's there right alongside the physics-based solvers. So you can very easily take your simulation results, which of course the data is already there, train an AI surrogate and get orders of magnitude speed up.
Yeah, exactly. And that's one of the areas we're investing heavily in at the moment, to bring a really cutting-edge product to the market that helps the designer with some agentic, not physics-based AI, but engineering-based AI to help with that setup.
Yeah, and we'll see some examples of that later.
Yeah, no, it's fine. And just kind of back on this point, the deploying broadly. So that's where we're helping a lot of our larger customers at the moment. For example, big automotive suppliers, they're using SimScale to put a simulation tool in the hands of the designers. So a high fidelity simulation tool that's easily templated and is very straightforward to use. In that respect, we're actually displacing a lot of the incumbent simulation tools that are more designed for specialist simulation experts, but aren't as easy for the design teams to use. So they're pushing that simulation capability earlier in the process so that they can iterate faster through the designs and essentially develop a better product at the end. And that's kind of following through into the AI capabilities as well. So I think, I will say this because I'm a SimScale representative, but I think we have the best end-to-end solution right now for AI, for simulation, for designers, because it's all in one user interface and it's an end-to-end solution. Yeah, so we can import any CAD file. So we support all the major CAD formats, and you can do some editing as well. So we have basic cleanup operations if you want to remove some embossing marks or delete holes, change some dimensions. You can easily do that in the tool. Sorry, Alex.
No. Thanks for that. Yeah, and we talked a lot about user experience, and of course, I think the feedback we get speaks for itself. We find that that's a really, really highly rated aspect of the platform. You can see those are the G2 recent G2 badges, and you can obviously read lots of reviews about the product. So this is what we're here to talk about today. How AI is really about to deliver some really transformative acceleration to engineering workflows. To a point where maybe at a certain point we'll be able to say, please design me a pump that meets such and such requirements, and that's sort of maybe ultimately where we're going to be going. But maybe to sort of ground things and think about how this relates to the AI tools that lots of us are using already. we can think about, the things that we use AI for today. We talked about right at the start: copywriting, design, coding. These are all so I guess one thing to think about is why are AI systems so good at these things? And one of the reasons is, they're trained on trillions of tokens. So there's such a huge library of training data available on the public internet for these kinds of things. And this is not really the case for engineering design. We just simply don't. There's sort of that kind of huge global data set doesn't really exist. So we're still doing a rather more complicated thing in engineering. So we're starting with some CAD. We're doing some engineering work to set up a simulation. We're then kicking off the simulation, looking at the results. And you can see that there's a human in the loop very much in that process. And of course, it's possible to, once you've built a kind of a pipeline workflow, possible to then execute that in an optimization study or something. But ultimately, that setup and that assessment is still requires the human in that process. So, what does that mean? Does that mean that we simply can't get from a prompt to a result in engineering? We think no. We think it is possible, but it just takes a slightly different approach. And if you think about what you would do today, maybe with an image generator, of course, this image was generated by AI. You can see there are, if you look closely, maybe some issues with it. Somebody there doesn't have a surfboard. There's definitely some slightly non-physical behavior here with what these two people are doing. But it's maybe I didn't specify my prompt well enough. I think I said I'd like 3 surfers surfing down a wave and others paddling out towards the wave. That was my prompt in this case. We kind of got 2.5 surfers. But it's no problem. So you can simply prompt it again and get a different one. So there's another one. I think that's only got 2 surfers. There's another person missing a surfboard. That one's pretty crazy. But eventually, you get to something that looks kind of decent, and that's sort of the process that we're probably more familiar with. But that's not really going to work for engineering. I think we need something rather more methodical. And so the way that we see this looking is, if we go back to this view where we're thinking about those steps, the CAD, the engineering, and the CAE analysis, there's really like two bottlenecks that we need to address there. So there's the CAE part, the actual simulation itself, which is kind of slow, I guess, using fundamental physics-based solvers. And then there's that engineering part, which is somewhat manual today. So that's really how we think about AI in SimScale. So we break it down into those 2 kind of categories when we're talking about it. We've got physics AI, which is the kind of deep learning surrogate model that predicts your simulation result more quickly. And then there's this like agentic engineering AI, which is more going to help you with your workflows and your model setup and that decision-making process and accelerate that side of things. And then, of course, if you combine those 2 things, then you can actually really unlock a serious acceleration. So we can dive into those in a bit more detail. The physics AI side, so I mentioned that's surrogate modeling. It is going to essentially allow you to predict your simulation results instantaneously if you have a model which is trained on the right kind of data. And what we're talking about today is a foundation model, which means a model which is pre-trained. So we have already trained this model on thousands of pump simulations, and it means that you can then use that as a sort of starting point, kind of a springboard, if you like, to then you could pick it up and use it straight away, or you could then extend the training data set with your own data. And of course, we have the infrastructure to build models directly in SimScale as well. And I think you're going to show that later, aren't you, Steve? Yeah.
Yeah, a bit later. I'll show you how we went through this process, the different steps that we took to build this first foundation model.
And so when we think about foundation models, in this particular case, we're talking about a centrifugal pump, but you can sort of imagine that if you have a sufficiently large data set, then that foundation model, it can kind of generalize across more and more pump designs. And so the more and more physics you could possibly add in, the more designs you could add in, you could eventually get to a kind of universal physics AI model in the future. And technology-wise, as I mentioned, the AI model training is really built into the SimScale platform, as you're going to see. So we can use a variety of deep learning frameworks. So we have Modulus, or actually it's now called PhysicsNeMo from NVIDIA, and Navasto at the moment. And those models are very easy to build and to manage and to deploy in your organization on the SimScale platform. The other thing that we have, which is fairly unique, is a very, very large community of open projects. So anybody can go and pick up the platform, open an account, and start running simulations that are public. And so we have over 600,000 users, including commercial and community users. And so some of that data is also available to build and augment models. So then the other side of it is the AI for engineering, so the sort of agentic side of it. And at the moment in the platform, we're really developing this very, very fast. So we're going to show you a little proof of concept in a moment that can help you set up simulations. So at the moment, we're really focusing on accelerating that manual work and helping you go through the model setup process and help you run models and then decide what to do next. And later we see that to extend to full design iterations where the model can go and then make changes to your CAD and explore more designs. And then we can start to actually do that design space exploration sort of autonomously. And here you can see there's a couple of examples of how this would work. So you would be interacting through a natural language interface with the platform, so with a little pop-up. And so that's using like a RAG LLM. And then you can have a conversation with the agent about what it's doing, and it can ask you questions, you can ask it questions, and it's quite a kind of collaborative relationship. So I think, yeah, now we have the demo. So I guess if I advance the slide, it's going to play the video.
I think so, yeah. Yeah. So this is a quick beta release that we've put together. And here the end user is uploading a PDF document with the requirements. This could be an RFQ for a pump design. And then the LLM is extracting from that the requirements and checking back with the user what the RPM should be for this setup. And then it's going ahead then and saying validate the setup. It's completed the setup for the simulation based on what was in the RFP document. And then it's suggesting that we already have a template for a turbo pump. So this is a foundation model, the foundation model that we've made available in SimScale, and it's recommending that to use it in this case. And then it's going ahead and using that foundation model. And the nice thing it's doing here now is it's doing an optimization loop using that foundation model. So rather than having to wait an hour for each simulation to complete, the foundation model is predicting the performance in seconds. So you can do an optimization in seconds to really hone in on the parameter space that would be of interest for this pump. So that's all happened through the interface. And then we're just asking it to run a full PDE solve as well. So it starts the full solve as well to validate some of the results that were obtained during that optimization run. And then as a final step, we would say, I would want this in a PDF report. and then the LLM would create a downloadable report of all of the steps that it's just gone through so that you could hand that over to the customer. So this is really focused on reducing that lead time that you have. We see a lot of pressure in the industry at responding to RFPs in time, and this helps provide a response in hours as opposed to days or weeks to that initial request.
So, yeah, so I think what you've just seen is really showing how powerful that combination of those two AI systems is. So we can really cover that whole workflow from the the CAD, the engineering stage, and the simulation stage, and that really allows you to actually totally collapse the kind of turnaround time for that entire study, kind of effectively to zero, really, compared with what it would take to do the whole thing with the manual work plus the kind of full solve for each design point. So we can talk a bit more about how you actually do that, like how you would build that AI model. And SimScale has this very unique built-in infrastructure. So the whole process, the data generation, the data preparation, the model training, the management, and then also I think being able to use the AI prediction and the simulation result kind of side by side in the same interface without having to do any moving things around or using two different tools or anything like that, all in one place. Typically, assembling this kind of tool chain with lots of different solutions would be a lot of work, and it's going to slow down how you can actually use that. So it's very easy, but I think what we often hear is it sounds really great, but maybe I don't have the time to invest in doing that model training. Clearly I need a decent set of data to be generated. I need to build the model, then I need to see if I'm going to get value from the model. So there's a bit of a kind of a leap to really get going with this technology, or maybe you're waiting for the right project to come along so that you'll have enough data to do it with. And then how do I know that it's going to be worthwhile if I actually go and invest this time? So that's really where I think a foundation model can really, really help to sort of turbocharge that adoption. And so the way I like to think about it is it's like going directly to base camp. We're not saying that it's going to take you all the way to the top of the mountain, but it's taking you to base camp, so it's much, much easier to then explore your surroundings and make an ascent to the top. You can pick it up and you can use it as it is. It's going to give you some decent results, and then you can also tailor it to your own designs, adding training data and make it more specifically focused to your own designs to get even greater kind of accuracy. So that's how we see foundation models impacting how you can actually pick up these tools and use them. Of course, we're talking here about a pump, centrifugal pump foundation model. But yeah, we also would like to introduce more of these for different kind of applications to give engineers a kind of a toolbox of starting points for using AI in simulation. So yeah, that's a kind of a brief introduction, take us up to what the foundation model is for. And Steve is going to take us through some demos. Fortunately, we can't do a live demo on the screen today, as we're kind of limited to using a pre-prepared deck. But we can also we can demonstrate this on a laptop afterwards for anyone who's interested. But we've got a series of videos that show the process.
Yeah, exactly. Thanks, Alex. So obviously we've seen the nice end result of how a AI LLM can interact with you, and then you can use an AI physics model in the background to make predictions and optimize a pump. What I'm going to show you now is how we've got to that point and how you could do this in SimScale as well. So let's have a look at the foundation model that we've built, how we got there, how we're going to do that for other pumps as well, and the technology that we're leveraging to actually make that possible. So the foundation model has about 50 different pump geometries in it. We've parameterized the design space, so we're exploring things like the blade angle, number of blades, the diffuser angle, the length of the diffuser, the length of the inlet, the scale of the pump, the type of the pump. But it's focused purely on centrifugal pumps. So we're looking at many different operating points and many different variables. And to do this, on this specific foundation model, we're leveraging some technology from NVIDIA. So 2 weeks ago, I was in California, NVIDIA's GTC conference, and we released this pump foundation model there. And essentially, it's an open CFD dataset that we've then trained on PhysicsNeMo to make it possible to predict the performance of a pump in real time. And this is something that's going to be continually developed by us. It's the first foundation model that we've released, and we're going to keep adding to it to improve it. And this is an extract of what we saw in the demo. So why is a foundation model useful? Well, it opens up the possibility to be able to do things like optimizing any new CAD for a pump in seconds as opposed to days or weeks. So the data points that you see being plotted on this curve, this is actually pretty much an exact real time of how quick this optimization can run. So what you're seeing here is actually an optimization algorithm with a CAD system in the loop. So the optimization is generating a CAD. That CAD is being uploaded to SimScale, and then the foundation model is being used to predict the performance of that pump at that operating condition. And then the optimization algorithm is taking the end result and deciding how to adjust the geometry for the next iteration. And through doing that, we hone in on the optimum efficiency region of the plot, where we can see the highest pressure increase at the highest efficiency. And then, obviously, we could validate those results by doing some full PDE, CFD results, just to make sure that we're in the right area. But it can get you to that region very quickly without having to investigate solving partial differential equations and doing CFD in this region, so you can purely hone in on the area of interest. So this is made possible using NVIDIA's technology. Unfortunately, our NVIDIA representative couldn't join us today, but he's passed on some slides for us to deliver. So I'm not NVIDIA. We're both from SimScale, but I'm going to deliver some slides here that NVIDIA gave us to present today. So I'm sure you're all aware of NVIDIA. Their core business is generating GPUs. And obviously, more recently, that has gone in the direction of creating supercomputers for processing AI. NVIDIA have really established themselves as the leader in the market for AI hardware. But also something that they do is they make some really great software libraries available. So the CUDA-X libraries for accelerated simulation. SimScale was actually featured in Jensen's keynote on the 18th of March for the work that we've been doing to accelerate simulation. So how does this work? Well, they have a tool stack of software that also is open source and available for people to integrate into their platforms. So there's various tools available there. Warp is used for design optimization. It can be used for doing virtual training of robot systems combined with Omniverse. CUDA-X is the library of solvers, so you can actually use NVIDIA to run CFD using CUDA-X libraries. There's the NIM, PhysicsNeMo, and Omniverse. So Omniverse, we use that for visualization and analysis, and that can be used to set up digital twins. And PhysicsNeMo is really the main tool that we've been leveraging for this foundation model. So that's an AI tool, and there's various libraries available in there. You can do pins and GNNs. The technology that we've been leveraging is graph neural networks, because that's the same tool that we've been using in the past. So we've been using Navasto, which has been in the AI space for about 2 decades now. They've worked extensively with big automakers like Audi. So we have that integrated on SimScale, and we now also have PhysicsNeMo. And we're using a graph neural network there to make predictions of what simulation results should be based on training data sets that we add in. So this is the library of CUDA-X capabilities that Jensen presented during the keynote. And the bit that we're zooming in on essentially is this part for AI for physics, the PhysicsNeMo libraries. PhysicsNeMo has quite a broad capability set. You can use it from various use cases, including additive manufacturing, computational fluid dynamics, structural analysis, geothermal analysis. There's many different use cases for it in the market, and many solver providers are leveraging this capability. It's not only SimScale, it's an open source code. And that's one of the things that we really like about it as well, because we're able to leverage it, we're able to put it out into industry, and NVIDIA are really happy to get the feedback back from us about how it's being used in real-world settings so that they can make changes and improve it and build a better library. So how this works is we use something from them that they've coined blueprint technology. So these various CUDA-X libraries are able to be delivered very easily by providers like SimScale because they provide a blueprint, which is basically a template of how it can be used with the interconnecting code required to implement it, all provided in the template. So we worked with NVIDIA, they provided us the blueprint for, in this case, Omniverse, and then it's very easy to add that in and make it available. So we started implementing PhysicsNeMo in January, and it's now available on our platform and in production. So within 1 month, we had a working prototype. Within 2 months, it was ready and it was deployed. So it makes it very quick. There's great support from NVIDIA for that. This is another example, slightly more complex, of the blueprint. I'm not going to take you through exactly every step of how this works. I'm also not fully familiar with this, but it's an example of how it's put together and how we've implemented PhysicsNeMo. Okay, so I'm going to show you now how we built this foundation model. And it's not rocket science. Anyone can do it. And that's the great thing about SimScale. This is an end-to-end solution. In some organizations, big companies, there's machine learning teams, AI teams that have been working on this for decades. And they have experts to collate the data, catalog it, and train AI models. You know, that's great, and it can work very well. But it doesn't provide one end-to-end, easy-to-use solution. The difference to what we've implemented here is anybody can do this. Any engineering team can create the training data they need, run the simulations, and then train AI models on that data and deploy them broadly within the organization. You don't need any experts in the organization to be able to do it that have learned about AI models or machine learning to PhD level. You just need CFD engineers, mechanical engineers to be able to run it. So, I skipped a few somehow then. Okay, so the first demonstration is on the CAD preparation. We're going to look at parameterization of the CAD. In this circumstance, we used Onshape. We have a good working relationship with PTC Onshape. It's kind of our equivalent in the CAD world. Onshape is also a cloud-based tool, just like SimScale. We have a tight integration. But it doesn't have to be Onshape. You could do this with Siemens NX, you can do it with SolidWorks, you can do it with FreeCAD, you can do it with any CAD application that has a API access. So the first step was to create the pump geometries. So here we're looking at an example here of how to parameterize a pump. We took a pump in Onshape and put in various parameters. So you can see we've got blade angle, blade thickness, blade radius, number of blades, diffuser length, diffuser angle, inlet length, and the scale of the pump. So all of these can be driven through an API script to create different pump geometries. And here you can see some examples of how this is done. So the number of blades in the CAD is parameterized to that number of blades parameter. And then when that's changed in the UI, obviously the number of blades changes in the CAD. The important thing is that this can be driven directly from the API. So it can be driven from an optimization algorithm, and then you can create thousands of different pump geometries from one pump original geometry. Now we took 50 of these geometries and parameterized them. So that gave us a very broad and wide data set that we could use to train the foundation model. There is still some limitations there. We always aligned the inlet with one of the cardinal directions. We always aligned the outlet with the same direction. We always had the rotating region in the same axis, and the impeller always rotated in the same direction. So there is some limitations there on the CAD. You can't put any pump orientation in, but it does mean that you can put in any centrifugal pump that works in that way. So we created this very large library. We ran thousands of simulations on that, and then all of that gets combined to create the foundation model. So that's the first part, the parameterization of the CAD. And I have to say, that's probably the most labor-intensive part of the process. What should happen, obviously, in a real-world situation is you already have all these CAD geometries built up over time in your engineering organization. You can just leverage those. But because we're generating a foundation model here, we had to create this data set artificially. So then the second step then is actually running the DOE studies. So essentially for each of those pumps, we started off a 200 simulation DOE study. Because SimScale is in the cloud, those 200 simulations can run in parallel, so there's no need to wait a long time. You can generate this sort of level of data set in a couple of days. With traditional tools, having to run sequentially, it might take months to be able to generate this data set. We were generating thousands of pumps in a single day. So I hate showing scripts in demos, but the nice thing about this, I think, is like literally that is the number of lines of code that were required to run a DOE. We used PyMu, open source optimization code. We're running 200 threads in parallel, and we're going to run 600 simulations in total. And it's really not an extensive amount of code, which is really nice, I think. And then so when this script runs, what you get generated in SimScale is a list of simulations with everything created programmatically. So once that script is run, you can go in and you can have a look at all of the simulations. Each one takes 31 minutes, and they all run in parallel. So within 31 minutes, you've created 200 simulation data points that you can use, and then you just go through and do this for all of the simulations. So it's frighteningly easy to create a very large data set of simulations in very little time. So yeah, they vary in runtime, some 30 minutes, some 15 minutes, depending on the number of blades that there are. So this is just showing, again, the post-processing image that you would see in the UI. But really, the UI isn't too important. You can use it to check the results, but we're leveraging these results then through the API mainly. Okay. And then the third step then is training. So this is one of the most difficult parts if you're going to be doing it independently of an end-to-end solution. Like SimScale, you need to have GPU infrastructure that you can train on. You need to have all the data pre-collated and tagged so that it can be used. But in SimScale, we take care of all of that automatically. One of the great things about using SimScale is you don't have to plan to use your simulations for AI. Just by generating simulations and using SimScale, you're already preparing to use AI in the future because we automatically save all of your data, keep it in a structured database, and then at any point you can switch on AI and you don't have to go back and clean the data at all. So here, I'm going to go to SimScale from a web browser, how I would always log into SimScale. Go to my dashboard. Here I can manage in my organization who has access to train AI models. And then if you have the right privileges, you just go in and create a new AI model. It's just like creating a new simulation. So you give it a name and start to set up that AI model with a description, and you can also add supporting files and documentation. So here I'm just setting it up, and then I say I want to select the projects to use for training. So then I go to my folder where I've been training the foundation models for the pumps, and I select the data sets that I want to use for that training. In this circumstance, In this circumstance, we're using 2 of those projects, and you can see there's 933 runs. And then I just give it a name and add the supporting information. So it's literally as easy as setting it up and pointing the AI algorithm at the simulation projects that you want it to use. We have some automatic tools to identify outliers in the data. This is really important to automatically detect those because maybe there's some failed runs or erroneous data sets, and they will have an impact on the performance of that model. When you want to deploy this out to the organization, you obviously want to have documentation that goes with it so people understand the limitations that I mentioned regarding where the inlet has to be, where the outlet has to be. And then here we can see the training that has been processed. We can see the training loss curve, how it's progressed through. And then we can actually deploy that. So we can see at this point, the foundation model is released to the community and everyone has access to it. Everyone in the organization can log in and make use of it.
Got to see who's used it there as well.
Yes, exactly. Yeah, so you can see this particular model has had 4,246 uses when I recorded this video last week. So that's mostly internal use at the moment, but also by our partners at NVIDIA, and we're making it publicly available as well now. Okay, so the final step then is how we deploy that model and make use of it. So we've been through how to create the data from CAD, simulation, how to train it, and now it's how we actually deploy it and make use of it. So again, this is within the SimScale platform. So I just showed that one was released. But we're kind of taking a step back here where this is what you would do. You would come in, you would analyze the data, see how the training had gone, and then the release process is as easy as just clicking release in the platform, and then everyone that is allowed to have access to that AI model will then be able to use it. So how it works then, as an example, you go in through the UI, you upload a new CAD geometry or start a project from an existing template that you have in your organization for designing pumps. So here I'm using an existing template that brings in a CAD geometry. And then to use the model, I literally select the AI model from the top drop down, and then we'll get an instantaneous prediction of what the different results are, pressure, velocity, predicted directly onto the CAD. And one of the critical things that we include here is a confidence rating. So this is really important when you're using AI. As I'm sure you know from using LLMs, things like ChatGPT, it will always give you an answer. It won't always be correct, but it will always give you an answer. And especially with chatbots, it'll give you a very confident wrong answer. So the important thing here is you see how confident the AI model is in that result. If you get a low rating, you know you need to retrain based on some more data in that parameter space. So I think, yeah, in this demo now, I've just changed the geometry. I've swapped it for a different geometry, and then I get an instantaneous prediction again. So you can see for a designer at an early stage, it's very quick and easy to iterate through designs, run what-if scenarios, change the number of blades, change the size of the pump, and get predictions on how that pump is actually going to perform. And then, yeah, we have another geometry. And then I think in a moment I change the inlet. So to something which is outside of the parameter space that this model was trained on. So a very high flow rate. This AI model doesn't know what to do with a flow rate that high. So there we see the confidence score is now very low. We get a confident result plotted in the display, but you can see it's complete garbage. It doesn't make sense. And the important thing is we see the confidence score. So we know that the AI model is extrapolating as opposed to interpolating within the data that it has. In this situation, what we would need to do is run a few more simulations. We wouldn't need to run too many more because we already have a well-populated foundation model. Run a few more simulations in that parameter space and then rerun the training part that I showed you to retrain this model, including that data. And then once that new model is available, publish it to the community and everyone can make use of it. We've already seen this video, so I won't play that again. This is the AI assistant, just helping us to do the same setup and respond to the RFP. So I showed it in the UI, but obviously the strength of this model that we've shown for running things like an optimization is the fact that this can all be run through the API. And as attendees of this workshop, you will all receive as a follow-up the Google Colab script required to run this optimization that you see here. Will provide you with access to the Onshape CAD model. If you don't already have Onshape, you can sign up for a free Onshape community account as a individual hobbyist, I think they call it. And we'll also provide access to you to the AI model in SimScale. We'll need to give you a professional trial to be able to do that. But please follow up with us and we'll provide you access so that you can literally recreate the exact same workflow that you've seen here using the foundation model that we're making available. And the idea here is that we want to open source this. We want to see what people can do with it and where they can go with it. So really take it, run it through its paces, see if you can build upon it. If you have some pump geometries, put them in, see what happens. If you're interested in training a new model, get back in touch with us. We want to hear what foundation models would be useful in the industry. So just to kind of recap, what have we seen and what have we been through? Well, we've seen how a foundation model can provide instant simulation results. We've seen how it can provide instant optimization. And Alex talked about how this can be a base camp for you to train your own model. So this foundation model, it's not going to work for all pumps. It's not going to give a great result for everything. But we've already put thousands of simulations in here. For you to train this on your pump designs, you only need to add maybe 100 simulations, and then you've got an AI inference model that works for your pumps. So we've done the hard part, and you just have to add in a bit more data. So we're pretty much on the limit. There's not much time for questions.
Is it already 10:30 now?
10:27.
Oh, yeah. Right. Okay. Well, thanks very much, Steve. I think that was really good. Really good demo. Showed exactly, I think, how to do this. So if we have questions, we're very happy to take those if we still have time to do that. But of course, you can grab us afterwards as well. We could just pop outside if you want to have a quick chat or a quick in-depth demo. We also have a stand in Hall 17 as well, sort of in the middle of Hall 17. So please do come and have a chat there later on if that would work better.